All right, so we're going to go through several pages of notes from the packet. I'm just going to review a little bit on this page. If you recall, the lines in blue here are the electric field lines. They point away from a positive, they point towards a negative. The electric field lines represent the direction a positive test charge would move if placed at that point. The dashed lines here are what we call equipotential lines, lines that are equal in their electric potential energy, and electric potential energy is voltage. And those equipotential lines are always at 90 degrees to the electric field lines. We have another 90-degree relationship to think about, and that is electric field lines always intersect conductors at a 90-degree angle to the surface. So right here where all these field lines come in, those are always at 90 degrees to the surface of this. Also, this charge here, you'll notice, always has the field lines leaving at 90 degrees from its surface as well. Continuing on, we're looking at charges here. In these two diagrams, the charge on the left is stronger than the charge on the right, and these charges have opposite signs. We know they have opposite signs because the field lines go away from this charge and the field lines go towards this charge. That means charge number 1 on the left is positive, charge number 2 on the right is negative. And if you count up, you'll notice my little blue dots here. You don't need to put those in your notes. But if you count up the number of field lines, and you count up the number of field lines here, you can learn about the ratio of charges. So on the left charge, when you count this up, there are 32 lines pointing away from positive charge 1, and there are only 16 lines pointing into negative charge 2. That means that the left charge, the positive one, is of magnitude 2 times the negative charge on the right. Here we have the same kind of thing, but an opposite relationship. Charge 1 is negative because the field lines point towards it. Charge 2 is positive because the field lines point away. And again, charge 1 has 32 lines. Charge 2 only has 16. If we look over at the two examples on the right, we find similar relationships. Again, ratio of 32 to 16 for the one on the left to the one on the right. That's a charge ratio of 2 to 1. These two charges are positive because the field lines point away. These two charges are negative because the field lines point towards. In both cases, there is a point here and here where there is no electric field and where a positive test charge would just sit there. No electric field means no force. No force means that if you just place it there and it's not moving, it will remain at rest. Okay, so the portion of notes that's underneath this rectangle, I want you to try that on your own right now. So pause the video, try that, and then we will uncover the rectangle and go over it. Okay, so here we go. Charge 1 is positive, same with charge 2, because charge 1 and charge 2 have field lines pointing away. Charge 3 is negative because it has field lines pointing towards it. Draw vectors at each point to represent the direction of the electric field at that point. We know this is the vectorial electric field because it's a bold E. So at point A, we have a little arrow here going in the direction of the electric field. These arrows are supposed to be tangent to the electric field line. So at point B, even though the electric field curves, The electric field at point B is a straight line. Vectors always have to be straight, although field lines can be curved, because these field lines don't represent the magnitude of the field, they only represent the direction. At point C, we go away. Point D, we're going away and tangent. Point E, in the direction of the electric field and tangent. Notice that I made my arrows roughly correspond to the magnitude of the field there. So point C, which was close to charge 1, which is a pretty strong charge because it has so many lines around it, this arrow is larger, this arrow is smaller, these arrows are somewhere in between. That leads us to a later question, which deals with the number of lines around. Which charge has the greatest magnitude? Charge 1. It has 24 lines coming out of it. The least magnitude is charge 2 over here with 8 lines. Charge 3 is in the middle with 16 lines. I put an X right here where there is no electric field. If you put a test charge there or any kind of charge there, it would just sit still. If you were to put a proton at point E, it would go down. Positive charges, like a proton, will go in the direction of the electric field. Remember, that's the definition for direction of electric field. The direction a positive charge would move. At point D, if we put an electron here, an electron will move in the opposite direction of an electric field. So instead of going up, an electron would move down at point D. All right, next page. All right, so we got some more with field lines here. Here we have arrangements of charges, and we are drawing field lines. I again marked points that had no electric field by using an X with a little circle around it. We've got a positive charge and 2 negatives here on the left. All of these are the same magnitude. The electric field is going to point away from a positive and towards a negative in the direction that a positive test charge would move. If you had a positive test charge right here, it would move down. It would either curve to the right or curve to the left. If it did just move straight down and go through this region, it would end up back here and then it would oscillate back and forth. That would have to be a very special situation, but it is possible. There's no E field somewhere here in the middle, and notice that this point is a little bit offset from the actual center between these two charges. The reason this is offset is because of this positive charge here. A positive test charge, if you placed it right here, would be attracted to both of those. That would cancel out. But a positive test charge here would be repelled by this. It would be repelled down, and so it would move down. A positive test charge here is going to be attracted to each of these negatives. So it is going to have a small amount of vertical attraction, which will be offset by the vertical repulsion from that test charge up top. So this is the point of no electric field. Notice how these lines curve, these lines curve. The ones on the outsides tend to be a little bit straighter. On the right, we've got 4 charges, 2 positives, 2 negatives. Again, the ones on the outside tend to be a little straighter. They point towards the negatives. They point away from the positives. In the very middle, we have no electric field. A positive charge in the middle would be attracted to the lower right and the upper left, equally canceling. It would be repelled by the lower left and the upper right equally, and those would cancel. So no electric field due to symmetry arguments in the very middle. These lines will be fairly straight, and most of the other ones will curve. All right, moving on. For the pictures at the bottom of the page here, the shaded region are conductors, the clear region are insulators. A little more information on that. In conductors, these are some of the key things to remember. E minus, that's the symbol for an electron. So an E minus charge is free to move inside of a conductor. Excess charge always resides on the surface of a conductor. There is no excess charge inside of a conductor unless there's a surface on the inside. There is no electric field on the inside of a conductor as long as it's in static equilibrium, electrical equilibrium. If there is an electric field on the inside of a conductor, which is possible, then you are not in electrical equilibrium, and there are charges flowing through the inside of the conductor. The electrons inside the conductor would flow in a direction opposite the electric field. And when you have charges moving inside of a conductor, we say that there is a current flowing. We'll get to that in a couple units. But it is possible to have an electric field inside a conductor. You just don't consider it to be in static equilibrium, electrical equilibrium at that point. And in this unit, we're only talking about equilibrium conditions. So no E field on the inside for this unit where we're in electrical equilibrium. And remember, the electric field is always perpendicular to the surface of a conductor. For insulators, there's another list of things to keep in mind. In insulators, the electrons, or the protons, are not free to move. An electric field can exist inside an insulator. We can talk about the reasons why in class. Ask me if you would. And the electric field does not have to be perpendicular to the surface. These 2 points here are kind of related to each other, and they have to do with the structural differences between conductors and insulators. So let's take a look at the diagrams at the bottom. The diagram on the left, we have a conducting slab here. We have an insulating slab here. Positive charge. All of these lines come off at about 90-degree angles, kind of radially. This positive charge will induce a charge on this slab. So we will have negatives on this side of the slab, positives on this side of the slab, and notice the difference in the distribution of these positives and negatives. On the bottom side, these positives are all equally spaced, and that represents the fact that the electrons, or the lack of electrons here, would be uniformly absent from their atoms, so that the atoms on the right, in the middle, on the left, they're all missing the same number of electrons, creating a uniform charge distribution. On the inside, however, closest to this positive charge, you're going to have more electrons. You're going to have a greater excess of electrons. Farther away, you will still have some excess electrons, but not as many as you do in the middle. So notice the spacing here. Bigger spaces towards the edge, smaller spaces in the middle, showing the charge density. The electric field will point away from this positive charge. It has to intersect this conductor at a 90-degree angle. So that's why these curve and they come straight in. This insulating slab, the electric field can go through it, and it does not have to be at a 90-degree angle to the surface. So those just end up being straight lines. For the diagram on the right, this is one that really threw people for a loop last year. There was a question similar to this on the first unit exam last year, one of the FRQs, and everyone did terrible on it. So I'm hoping that we'll go over it a little more thoroughly this year, and that if there's a problem like this, it won't throw you for such a loop. So you could think of this material here as a conductor. It could be part of a sphere, like this could be a cross-section of a sphere, or this could be a hoop or a cylinder or something like that. Inside of it, we have a positive charge. That positive charge is going to induce a separation of charge in the conductor. The conductor has no net charge, and so the amount of negatives that you get on the inside is going to be equal to the amount of positives that you get on the outside. I think I tried to do this right. So I've got 1, 2, 3, 4, 5, 6, 7, 8 negatives on the inside and 8 positives on the outside. Again, the spacing represents the charge density and the distribution. So on the outside, all these positives here are equally spaced, showing that the charge density is uniform on the outside and the charges are all separated by an equal amount. On the inside, however, that's not the case. Because we have this positive charge which is offset, there is going to be a higher concentration of free electrons over on the right, and there will still be some free electrons towards the left, but less of them. If this charge were in the very center, and only if it was in the very center, then we would have a uniform distribution on the inside as well as the outside. So pointing away from this positive charge in the middle, we have our electric field lines, because that's the direction a positive charge would move, is away from another positive charge. These have to curl in such a way that they make 90-degree angles with the inside of the conductor, and they must depart from this little circle at a 90-degree angle as well. Inside the conductor itself, there is no electric field. There's no electric field inside the conductor, because if there were, then free electrons would move there and you would have current and you wouldn't be in equilibrium. Outside the conductor, we again have field lines pointing away from the positive charge on the surface, and they again are at 90-degree angles here, and they are evenly distributed around the outside. All right, we're not going to do much on this page, but I do want you to be aware that when you see MC, that means millicoulombs, that's times 10 to the negative third. Microcoulombs is times 10 to the negative sixth. Nanocoulombs times 10 to the negative ninth. Picocoulombs times 10 to the negative 12th. Femtocoulombs, which would be FC, would be 10 to the negative 15th. I don't know 10 to the negative 18th. It's not that common. And positive exponents have their own name as well. Like kilo is times 10 to the positive third. Mega is times 10 to the positive sixth, etc. So we have 1 millicoulomb here, negative 1 millicoulomb. That is negative 1 times 10 to the negative third. This is 36 times 10 to the negative sixth, and 100 times 10 to the negative sixth. 100 times 10 to the negative sixth is 0.1 times 10 to the negative third. So this 100 microcoulombs is 0.1 millicoulombs. There are 1,000 microcoulombs in 1 millicoulomb. So this is 1,000 microcoulombs. I want you to take a guess as to the direction of the electric field at point A here due to this arrangement of charges. So think about the direction of the individual electric fields from each of these three charges, and then which one's going to be stronger, which one's going to be weaker, and after you add them all up, which direction is the overall electric field going to point. So take a guess at that now. Okay, moving on. There's only one other thing we're going to fill in on this page, and it is down here. When you are far away from a group of charges, then we approximate the electric field as that of a point charge equal to the net charge of that charge arrangement. So When you are far away, the electric field is K Q net over R squared. It's going to be in the r hat vector direction, although you can just think of it as pointing away from a positive net charge and pointing towards a negative net charge. And the net charge is the sum of all the individual charges, so Q1 plus Q2 plus Q3, all the way up into Qn, which would be your last charge, and that's why it's also the upper limit on our summation symbol. So that's all for this page. Let's move on to the next. All right, so on this page, I'm going to go through the top 4 examples with you, and then you're going to do the bottom 4 examples on your own. I'll move this rectangle, and we'll see how you did. A couple things to remember here. You are supposed to draw arrows representing forces for each assembly. State the direction the center of mass will travel, up, down, left, or right. Remember the acceleration of the center of mass, since these are still to begin with, is going to be in the same direction as the net force, regardless of any rotational effects. The motion of the center of mass is always governed by the net force. And you're going to state the direction of rotation, clockwise or counterclockwise. Remember, clockwise using the right hand rule. If you curl your fingers in a clockwise direction, your thumb points into the page, and that's like in the back side of an arrow, the feathers of an arrow going away from you into the page. Curl your fingers in a counterclockwise direction, that is out of the page, and this little symbol here is like a tip of an arrow coming straight towards you, out of the page. The sum of the torques is I alpha, so whichever direction the net torque is, that's the direction the assembly is going to rotate. I color-coded mine. It'd be great if you color-coded yours as well. So I did all my forces in blue, and all the torque and rotation stuff I did in pink. I realize I made a little mistake on this first one. A positive charge moves in the direction of the electric field to the right. I must have not seen the negative when I went through this at first, because a negative charge would really move in the opposite direction of the electric field. That would move to the left, and moving to the left here would create a clockwise rotation, and we would have an overall clockwise rotation. And the center of mass, if one force went to the left and the other force went to the right, they would cancel off and the center of mass would not move. So let me fix up those mistakes and then we'll move on. All right, so here's how this first problem should have really looked. This stuff was all correct. For this negative charge, it's going to want to move up the electric field. Negative charges always move in the opposite direction as the electric field points. The center of mass is right in the middle. This is going to cause overall a clockwise rotation. Both of these will. Remember, torque is R cross F. R is the vector that goes from the center to the point of force, and then you cross that with F. So if you point your fingers in the direction from the center down to the bottom, and then you curl your fingers in this direction, your thumb points into the page. Same thing here. If you point your fingers up towards positive Q, and then you curl your fingers to the right, your thumb will also point into the page, which is a clockwise rotation. So make sure you've got the corrections set on this one, and then let's look at the next couple. Okay, we'll hope there's no more mistakes here, but we'll correct them if there are. A positive charge moves in the direction as the electric field. Another positive charge moves in the direction of the electric field. This one is going to create R cross F. That's going to create a counterclockwise rotation out of the page. This one is going to create R cross F. That's a into the page clockwise rotation. Because these two forces are equal and these two radiuses are equal, those torques will cancel each other out. We will have no angular acceleration, and our center of mass will move straight to the left since both of our forces are to the left. So we add them up and we get an even greater force to the left. Next, we've got a positive charge with a movement in the direction of the electric field, a negative charge, which is going to move in the opposite direction. Notice this arrow is longer than this arrow because this charge is twice as big. So I tried to make this arrow twice as long. Again, R cross F gives us a clockwise torque here. Down here, we also have R cross F giving us a clockwise torque. Both torques are clockwise, and so the angular acceleration will be clockwise. The center of mass is going to move to the left because if you add up this force and this force, the force to the left is greater, so the net force will be to the left, and that's the direction the center of mass will move. One more, and then you'll do the bottom ones on your own. In this last one, we have a negative charge, which is going to move in the opposite direction of the electric field, a positive charge, which moves in the same direction as the electric field. This has a value of 2q. So I again made this arrow twice as big as this arrow because there's only a single q here. When you do R cross F, since R and F are in the same direction here, the angle between them is 0, and a cross product is based off of the sine of the angle between the two vectors. So RF sine theta would be R times F times sine of 0. So our no torque there for this exact same reason, no torque over here. R cross F times sine of 0 gives us 0 torque. Overall, we have more force to the left than we do to the right. Net force is to the left, acceleration's in the same direction, and the sum of 0 torque and 0 torque is still 0 torque, so no net torque there. You're going to pause this now, and you're going to fill in the bottom 4 examples on your own in this same fashion. All right, for these bottom charges, positive charge moves in the direction of the electric field. The radial vector here would be R cross F. They have 180 degrees between them, and sine of 180 would be 0. Here, R cross F has a 0 degree angle. Sine of 0 also gives us 0 torque. No net torque, no angular acceleration, and since both our forces are up, our acceleration is going to be up as well. In the next example, we've got a negative charge moving in the opposite direction of the electric field, a positive charge moving in the direction of the electric field. Because these angles, again, are 0 degrees, there's going to be 0 torque. We have one downward force and one upward force of equal magnitude, so no net force, no net torque, no acceleration, linear or angular. In the third example, we've got a negative charge wants to move opposite the direction of the electric field. A positive charge wants to move in the direction of the electric field. Because this charge is twice as big, I made the force arrow twice as long. The angle between these is 180 degrees in both cases. Sine of 180 is 0, so no torque, no angular acceleration. Because our upward force is greater than our downward force, our net force is up and our acceleration is in the same direction. The last example here, we have a negative charge that wants to move in the opposite direction of the electric field. Another negative field charge which wants to move in the opposite direction of the electric field. This charge is twice as big in magnitude, so this arrow is twice as long. It's going to have twice as much force. The torque here, this R cross F, if you point your fingers from the center towards negative Q and you curl your fingers up, your thumb points into the page, that is clockwise torque. Here we have the opposite, R cross F. Your thumb would point out of the page. That's counterclockwise. Because this force is bigger and these radiuses are equal, this torque is going to be bigger. So when you add them up, they will cancel some, but our net torque is going to be counterclockwise, and so our angular acceleration will follow suit. Also, both of these arrows point up. When you add them together, you get an even greater force up, and so the acceleration is going to be up as well. That's all we're going to do on this page. The rest of this page, this stuff at the bottom here, we will do in class on Friday. All right, next page, Coulomb force and Coulomb's law. If you have two opposite charges, like a positive and a negative, they attract each other. So the force on the negative charge would be towards the positive. The force on the positive charge would be towards the negative charge. And if you have two positives, this would also work for two negatives. Then you have a repulsive force, and the force on one positive is going to be in the opposite direction as the other positive, and you'll have the two forces pointing away from each other. In an attractive case, the two forces point towards each other. So two vector expressions for force. These are related to each other. The one on the left here is a little bit simpler, so I'll talk about that first. We have here vector F with subscript Q. That is the force experienced by charge little q due to charge big Q. Okay, so force on little q due to big Q. And that force is equal to K times Q, which is the magnitude of the big charge, not just the magnitude, it would include the sign as well, times little q, which is the value of the small charge, including the sign. So if these are negatives, you gotta plug in a negative there. On the bottom, we have r squared, which is the distance between them. And then we have an r hat vector here with big Q, little q subscript. That's a unit vector that points from big Q to little q. A unit vector is a vector of length 1. So when we multiply this by a unit vector, we don't change the size of this. All we do is use this unit vector to indicate a direction. And if Q, big Q and little q, if those are opposite signed, one positive, one negative, then a positive and a negative will make this whole expression negative. And when you multiply negative times this r vector, you find that your force is in the opposite direction as the r vector. And we can see that up here, the r vector points away, but our force points towards, which is the negative direction of the r vector. So this is the vectorial form of Coulomb's law. These subscripts can be difficult and tricky to keep track of. So an easier way to think about this is just to think about the magnitude of the force as being the absolute value of kqq over r squared. And then you should think separately about if it's an attractive force or a repulsive force, and you can put a plus or a minus in front of this depending on whether your force is in a positive or negative I, J, or maybe K direction. Okay? But just because Q times Q comes out to be negative doesn't mean that your force is necessarily in a negative direction, because the R vector here could be in a negative direction, and then a negative times another negative for your R vector would end up being like in a positive direction. So don't think about this vector equation too much. It's a formality. Instead, think about the magnitude of the force and then think separately about, is it attractive or repulsive? Which direction does it actually point on my coordinate system, whatever coordinate system you're using? We have another vector equation for force, which is the same thing as this one on the left. The only difference is that instead of having this K on the top, we have a 4 pi, and then this funny looking backwards E with the little 0. That is called epsilon naught. Epsilon is a Greek letter. So 4 pi epsilon naught times r squared on the bottom. Because these are equal to each other, k must be the same as 1 over 4 pi epsilon naught. The subscripts here mean exactly the same thing as the subscripts over here. And again, don't worry too much about the vector form of this equation. You should be thinking magnitude of force and then think about the direction separately. Use your common sense. Is it attractive? Is it repulsive? Is the force going to point up, down, left, or right? And is that in the positive or negative I or j direction depending on your coordinate system? The value of k is 8.988 times 10 to the negative 9th, and the units for k are Newton meter squared over coulombs. Actually, I believe that needs to be coulombs squared on the bottom. Okay, so please right here, make that a coulomb squared, because if you think about this, we have coulombs times coulombs on the top. That's coulombs squared up on the top. You need to cancel it out with coulombs squared on the bottom. Here we have a meter squared on the bottom. That would cancel out with meters squared on the top, and we would be left with units of newtons, which is what we should have for force. So that's a little mistake. This should be coulomb squared. Just like this one is coulomb squared up on the top, this is coulomb squared on the bottom. This k is called Coulomb's constant. And the reason this equation is a little bit easier to use is because there's less stuff to type into your calculator. You only have to put k in once and it's on the top. Here, you have to put a 4, you have to put a pi, and you have to put an epsilon naught, and they're all on the bottom. We will be using epsilon naught for plenty of other things here, but for Coulomb's law, it's easier to use Coulomb's constant. Basically, anytime you have an epsilon naught in an equation, you could use a k, or anytime you have a k, you could use an epsilon naught by the relationship that k equals 1 over 4 pi epsilon naught. It's just a matter of which one's more convenient. So Coulomb's constant, you can kind of think of that as like an adjusting factor, like a gravitational constant, big G, right? Adjusted the value of m1 times m2 over r squared. It adjusted that value to make it equal a force. Here, we're adjusting the value of q times q over r squared by some amount so that this stuff actually equals the force. So this is just a proportionality constant. Epsilon naught, also a proportionality constant. It's 8.854 times 10 to the negative 12th Coulomb squared over Newton meters squared. That is called the permeativity of free space. The permeativity of free space has to do with how electric fields permeate through empty space, through a vacuum. Now, it turns out that electric fields behave differently. They permeate differently. They have the ability to penetrate differently depending on the substance. So an electric field in glass behaves a little bit differently than an electric field in air, which behaves a little bit differently than an electric field in water, which behaves a little bit differently than an electric field in a piece of wood or a piece of plexiglass or anything else. So each substance has its own permeativity constant, and that's why when you look at something through a glass, like when you look at something that's in water inside a glass, like a straw, it gets bent at the surface of the water. There's like a jump in the straw. It's because light is made up of electric fields, and electric fields work a little bit differently in glass and in water than they do in air. It's the same reason that a prism is able to split up the spectrum. It's because of how the electric fields in each individual color of light behave a little bit differently in glass than they do in air. All right, moving on down the page here. In the diagram above, both charges have the same magnitude of force acting on them, but in opposite directions. They either point towards each other or they point away from each other. These are Newton third law pairs, right? Equal forces in opposite directions. Forces are always created between two objects that exert forces on each other, and the forces they exert on each other are always equal in magnitude but opposite in direction. The elementary charge E is the magnitude of the charge on an electron or a proton. An electron is symbolized by E with a superscript of minus. A proton has an E with a superscript plus. This E here is just a magnitude. Don't think that E stands for electron. E minus is for electron. The value of E is 1.602 times 10 to the negative 19th coulombs. A coulomb is kind of like a kilogram. It's a unit of charge. Okay? And 1 coulomb is approximately 6.24 times 10 to the 18th electrons. Now, times 10 to the 18th is a huge amount of electrons. Times 10 to the 6th is a million. Times 10 to the 12th would be a million. And times 10 to the 18th is a million. You could also think of it as a billion. Those words might not mean much to you, but needless to say, they represent very, very large numbers. When you rub your hair and you get some static electricity built up on a balloon, you might have on the order of a charge of like 10 to the negative 6th coulombs. So to get from 10 to the negative 6th up to 10 to the 18th is a huge difference. Continuing on, the rules that we just learned look very much like Newton's universal gravitation. The only difference is that Coulomb's law lacks a negative sign, and electric charges can be different. They could be plus or minus. Gravitational charges, masses, always have to be positive. And so the Coulomb force can also be repulsive, which is not the case with gravity. Gravity was always attractive. So in the gravitational force equation, in its vector form, you find a negative here to symbolize the fact that it's an attractive force, and the force on mass A is in the negative of the radial vector, which points from B to A. For our electric force, if one of these two charges is negative and the other is positive, then we get positive times negative. We'd get a negative out in front, and that would again be an attractive force. If these are both positive, or if they are both negative, then this overall expression stays positive, and it's a repulsive force which goes in the direction of the vector from the charge which is creating the force to the charge that's feeling or experiencing the force. That's it for this page, so let's look at the next one. All right, I again color-coded my work here. If you want to do the same thing, that would be great. We have two main charges here. We have a plus 4q positive charge and a minus q negative charge. I circled this one in blue. I circled this one in pink. So all of my pink arrows here are charges from this negative q charge. All my blue arrows are forces from the plus 4q charge. And the black arrows are my net force. So when we have a positive test charge close to a positive 4Q charge, we're going to experience a repulsive force. Meanwhile, this negative Q charge has just a tiny amount of attraction. So if you imagine taking this pink vector and putting it tip to tail with this blue vector, this pink one will make the blue one a little bit shorter, and it will make it move a little bit to the right. So our net vector here is the sum of the pink and the blue vectors. A test charge over here, positive, would experience a large attractive force because it's so close to this negative one. This charge is pretty far away, so it experiences a little bit of repulsion, and the net force would be to the left and it would still be pretty big. I did make one mistake that I notice here, and that is the length of the pink and the blue arrows. The blue arrow here should be bigger, roughly 4 times bigger than the pink arrow. So please, when you copy this down, make either make your pink arrow shorter here or make your blue arrow a little longer. They both point to the left. We have this was a negative charge in the middle here. These other ones were positive. This one was negative too. So we have a negative charge here. It's an attractive force to the plus charge. It's a repulsive force from the minus charge. Both of those point left, so our net force is going to be left. Let's take a look at the next example. Okay, so you've got a charge Q, which is placed between two other charges of Q and 9Q on the x-axis. Each tick mark represents a distance of L, and we're going to come up with an expression for the net force on charge Q, this one in the middle. It's at x equals 0, and we should make it in terms of Q, Q, and L, and what other fundamental constants we need. It's important to realize that this Q here is positive. If this Q was meant to be negative, you would see a negative in front of it, okay? So the Q represents the magnitude, and the fact that there's no negative sign in front of it tells us that it's positive. We have a radius of 6 units over here. We have another radius of 6 units over here. You can see I color-coded so that all of the forces involving this positive Q, I did in blue. All of the forces involving this 9Q, I did in pink. It would be great if you color-coded yours as well. Our net force is the force due to this charge plus the force due to this charge. The force here, positive and positive, is going to be repulsive. It's going to point to the right. The force from the 9Q charge, positive and positive, it's going to repel to the left. Because we have equal radiuses and 9Q is a lot bigger than 1Q, this repulsive force is going to be much bigger than this repulsive force. So we fill in KQQ over R squared. The blue one is positive because it's going to the right. The pink one is negative because it's going to the left. So that's where this negative sign comes from. This was a vector form, and I've shown the vector now by putting a negative sign there. I don't need to put eyes with these because it's a one-dimensional problem, so everything is in the same I direction. Square the bottoms. We're going to collect up like terms. We get negative 8 over 36, and we simplify that to be negative 2/9. And the negative means it's a net force to the left. What's the electric field here at x equals 0? Well, our electric field is defined as being force per unit charge. So I divide the force by this charge at that point. Don't divide it by the big charge. That would be the electric field at this point due to this charge. We want the electric field here at x equals 0 due to both of these big charges. So I divide by little q, those cancel out, and I end up with negative kq over 9L squared, and it is also to the left. The net force and the electric field will always point in the same direction. Well, I guess I shouldn't say that. They will either point in the same direction or they'll point in opposite directions. It depends on if the charge that you're dividing by here is positive or negative. Our next question was, where do we move charge little q to on the x-axis so that it experiences no net force? And there is an algebraic way to figure this out, but it's kind of complicated, so I'm taking a conceptual approach. The forces on the little charge q will be equal when the 9q charge is 3 times farther away than the single q charge. This is because of this r squared that's on the bottom of the Coulomb's law equation. So when you square something that's 3 times farther, you get 1/9 the amount of force. And because this charge was 9 times larger, it's going to have 9 times the amount of force. So if we want to reduce the force by 1/9, we have to move it 3 times further away. Where does that happen? Well, it happens right here at x equals -3. If we put charge little q at x equals -3, we then have a radius of 3 to the single q charge, and we have a radius of 9 to the 9q charge. So 9 is 3 times as big as 3. So now the distance to the 9q charge is 3 times larger than the distance to the single q charge. So let's just check and make sure that the magnitude of those forces is equal. We substitute in for the radiuses. You can see this would become 9 squared. That's 81. 9 over 81 becomes 9. And this one is 3 squared, which is just 9. So they end up being the same. And we know they're in opposite directions because positive and positive repels. Positive and positive also repels. So the forces go in opposite direction. They're equal in magnitude, so they will cancel each other out when they add up. What's the electric field at this location? Where there is no force, there is no electric field. So the electric field equals 0. That's always an easy one. We got one more example similar to this that we're going to look at on the next page, and that'll wrap it up. All right, so we again have a positive charge little q placed between 2 other charges. This time we have a negative q over here on the left, and we still have 9q over here on the right. I'm still color coding so that the negative q is in blue, the 9q is in pink. The radiuses here are still 6L to start off with. Looks like I forgot an arrow on my pink arrow there, an arrowhead on my vector. So positive charge here, that's a repulsive force. Negative charge here, positive charge here, that's an attractive force. So they both point to the left. The left in this case is a negative direction. So that's where this negative and this negative sign come from. I also see that in my haste, I should have put right here, this should be a 9q and then the other q. So make that happen on yours. You can see that I remembered the 9 right here. I forgot to put 9q in here. And goodness gracious, I must have been working at this too long because I also forgot my L squared right down here. So there's an L squared. So that's a change right there, L squared. This should be 9 big Q little q. -1 and -9 make -10. 10 over 36 becomes 5 over 18, and that points to the left. The electric field at this point is force divided by charge. You're dividing by the charge that's experiencing the force, so we're dividing by little q. When we do that, the little q's cancel. Again, this points to the left. The second part to this question is similar to previously. Since we want our forces to cancel, the forces will be equal when the 9q charge is 3 times further away than the single q charge. And that happens when x is at -12. Why is it different than last time? Well, it has to do with the fact that our positive and negative charges aren't the same. We have a negative q here, and that's going to provide an attractive force. And this positive 9q provides a repulsive force. So that means that if our charge q were anywhere in here, it would be getting pushed to the left from the 9q, and it would be getting pulled to the left from the negative q. It's not until we're on the other side of negative q that our blue vector becomes an attractive force to the right, and the pink vector becomes a repulsive force to the left, and then they can cancel each other out. That's the only region in space where those two vectors have a kind of push-pull relationship like that, where they can cancel out. If you were over here in space somewhere, then the 9q charge, which we would be very close to, would have a very great repulsive force out to the right. The negative q charge would have a very tiny attractive force to the left. And although they would be in opposite directions, they are not going to be equal, because as long as you're to the right of the 9q charge, you're always going to be closer to the 9q charge. And we need the 9q charge to be further away. So our only option is to be over here on the left. You can see how this works out. The radius to the 9q charge turns out to be 18L. The radius to the single q charge turns out to be 6L. 18L is 3 times as big as 6L. I didn't write down the math to show that the forces are equal, but it would work out just the same as last page. Again, electric field is force per unit charge, and if force is 0, then electric field is 0. That's always easy, so keep that in mind. We got one more problem at the bottom here that we look at, and that is it. So down here, we've got a square arrangement of charges. We're calculating the net force on a charge of -q, which is at the top right corner of a square. All 4 sides are the same length, r, and the opposite corner is also -q, opposite to this one. So -q at top right, -q bottom left. The other corners have charges of +2q. So positive 2q top left, positive 2q bottom right. Because this is a negative and these ones are positives, we're going to have attractive forces, and a negative here would have a repulsive force. We'll need to know the hypotenuse of this, and the hypotenuse of a square is rad2 times the side length. So force number 1, which I'm calling the force on the -q due to the positive 2q up at the left corner, that's -2q times q over r squared in the I direction. It's negative because the force is to the left, and it does not have a component going up or down in the j direction. The force on the -q charge due to the other 2q charge at the bottom is very similar, but just in a different direction. So 0 in the I direction and a negative k 2q q over r squared in the j direction. Force number 3 is a little trickier because it's not in the I or j direction. So we do kqq over r squared, and r this time is the diagonal of our square. So it's rad 2 times r squared. And then the I component of this, I'd multiply by cosine of 45 because this force here is at a 45-degree angle. That's what you get when you cut a square in half. Similarly, the y component or the j component multiplied by the sine of 45, same thing as cosine of 45. It all works out to be the same by symmetry. As we simplify this, cosine of 45 is rad 2 over 2, same as sine of 45. You can see I squared the bottom of this to get 2 times r squared, 2r squared. And then this 2 and this 2 multiply together to give us 4r squared on the bottom. We have a rad 2 on the top. And of course, q times 2 is q squared. So now I need to add all 3 of these forces together. You notice my coordinate system defined down here. And I said the origin is at the negative q charge. So that's 0, 0 right there. Although it wouldn't really matter exactly where 0, 0 was for this problem. When we add these together, since we have a denominator of 4, I'm going to need to multiply this vector by 4 over 4. The 4 on top multiplies with this 2 to give me an 8 on top. That's where this 8 comes from. Look, 8 over 4 is 2, and that's what we have on top here, 2. And it was negative, so that's why the 8 is negative. This one was in the positive I direction, which I forgot to put another I right there, so I just added this I in. I forgot that little vector. Same thing happens in the j direction. This one in the positive direction. This one's in the negative j direction. Same thing with the common denominators. And then if you wanted to evaluate this and get a little bit more of a decimal approximation, because sometimes it's hard to understand or think about what a rad minus a number is going to be. Which one's bigger? Is it going to be positive or negative? Well, we know that the force should be negative because this going down is larger in magnitude than this one going up, because this distance here is shorter than this distance here. And this one going to the left is bigger than this one that goes up and to the right, because this distance is shorter than this distance. So we should expect that both of these are negative, which they are, and they're negative 1.65 kq squared over r squared. And that's it. So make sure you got everything in here. Let me know if you find any mistakes or if you have any questions about anything. And I'll see you on Friday. Have a good one.